and good morning, dear students. Today we are going to study next point of chapter number 2, which is change in entropy during reversible process. First of all, you already know what is mean by reversible process. Reversible process is the process in thermodynamics which can be reversible in exact opposite sense. Now, for this reversible process, we have to find out change in entropy. Uh, Example of reversible process is Carnot cycle. So Carnot cycle, Carnot heat engine, you will study in next chapter, which is chapter number 3. So when you study that Carnot heat engine in chapter number 3, there you are going to study Carnot cycle. Here I am going to take directly example of Carnot cycle. Okay, and I am going to give rough explanation about Carnot cycle. So first of all, Carnot cycle, if you look into indicator diagram of Carnot cycle, so indicator diagram is diagram of pressure and volume. Okay, so this is PV diagram. So in Carnot heat engine and Carnot cycle, there are 4 processes. First process is isothermal expansion, which is C1 to C2, which is takes place at temperature T1, and heat energy Q1 is absorbed during this process. Then adiabatic expansion, which is C2 to C3. So here there is no amount of heat energy is absorbed or rejected. So that is adiabatic expansion. So if you look into definition of adiabatic expansion or compression, adiabatic process is the process in which there is no exchange of heat. Now, third process is isothermal compression. So isothermal compression is the process which is from C3 to C4. That process takes place at temperature T2 and amount of heat rejected by the system is Q2. Last process is C4 to C1. So this process is again adiabatic compression. So in Carnot cycle we have, now this is a reversible process, means if you go from C1 to C2 we can retrace back same path from C2 to C1. So C1 to C2 is isothermal expansion. So here we can write steps involved in Carnot cycle as first one is C1 to C2 is isothermal expansion. Okay, so at temperature T1 and heat absorbed is Q1. So C1 C2 is the isothermal expansion at temperature T1 and amount of heat absorbed is Q1. C2 to C3 is adiabatic expansion. Now during adiabatic process there is no exchange of heat. So dq is equal to 0. C3 C4 is isothermal compression. At temperature T2 and heat rejected is Q2 during C3 to C4 process. Last one is C4 to C1 is adiabatic compression. There is no exchange of heat. So that is dq is equal to 0 for C4 to C1. So see, we have four processes C1, C2, isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. So all the four processes are I have explained over here. Now we have to find out change in entropy. Now if you start from C1, so we go like this, okay, and again came back at C1, and from C1 the cycle repeat itself again and again. That's why this process is known as cyclic process or reversible process. Here we know that change in entropy of system. Now for system we know that equation for change in entropy ds is dq upon t. Okay. Now ds is change in entropy, dq is amount of heat energy absorbed or rejected, T is temperature. Now for that system, if amount of heat energy absorbed, okay, then we can take dq as a positive term, and if for that system amount of heat energy is rejected, then we can take dq as a negative term. So again, for C1 to C2, change in entropy we are calling that as S1 is equal to, now from this equation dq means amount of heat energy absorbed. Now see, from C1 to C2 process amount of heat energy absorbed is Q1. So this is Q1 at temperature T1. So change in entropy is Q1 upon T1. Okay. Now for C2 to C3, change in entropy S2 is equal to. Now see, for C2 to C3, which is adiabatic expansion, there is no exchange of heat. So dq is equal to 0. Now in this equation, if you put dq is equal to 0, then ds is equal to 0 upon t. So this is 0. Okay. So for C2 to C3 process, there is no, we can say, change in entropy. Entropy remains constant. Now for C3 to C4 process, change in entropy is S3 is equal to. Now C3 to C4 process, which is isothermal compression, amount of heat energy rejected is Q2 at temperature T2. So our equation become minus Q2 divided by T2. So this is our equation number 3. So for C3 to C4, change in entropy is minus Q2 divided by T2. Now last one is C4 to C1, change in entropy, which is S4 is equal to. For process C4 to C1, dq is equal to 0, means there is no exchange of heat. So for that S4, again if you put dq is equal to 0 in this equation, then this is 0 and this is equation number 4. Now if you combine all the four equations for whole Carnot cycle, change in entropy delta S is equal to, here you can write S1 plus S2 plus S3 plus S4. Now this is equal to, if you add all these four quantities, so that will become Q1 upon T1 minus Q2 upon T2. Okay. So call this as equation number 5. So we have taken from equation 1 to 4. We added all the four equations. Again, for Carnot cycle, we are going to derive relation for Carnot cycle in chapter number 3. So we are using that relation. For Carnot cycle, Q1 divided by T1 is equal to Q2 divided by T2. So this is the equation we are going to derive in next chapter. So if you put Q1 upon T1, which is over here, is equal to Q2 upon T2 in equation number 5, if you put that in equation 5, we will get delta S is equal to, see, Q1 upon T1 is equal to Q2 upon T2. So delta S is equal to 0. So if you take reversible process, you can put suffix R over here. For any reversible process, change in entropy is 0. Okay. So reversible process is also known as isentropic process. We proved that for Carnot cycle. Now we are going to study change in entropy during irreversible process. Or this process, or this is also known as principle of increase of entropy. So before that, I forgot one thing. Okay, sorry about that. Here I have shown you that change in entropy during reversible process for Carnot cycle. This is for system. Okay. Now remember, definition of universe is system plus surrounding. Okay. Now to find out change in entropy of universe, we must find out change in entropy of surrounding. Okay. Now to find out change in entropy of surrounding, again for surrounding, see, Q1 is the amount of heat energy absorbed by the system. Q1 ही जी amount of heat energy आहे ती काय केलेली आहे सिस्टमने absorb केलेली आहे. म्हणजेच काय केलं असेल सराउंडिंग ती हीट एनर्जी रिजेक्ट केली असेल. ओके, इथं काय करणार आपण चेंज इन एंट्रोपी ऑफ सराउंडिंग. Here for C1 C2 during this process, change in entropy S1 is equal to surrounding साठी आपण सिम्बॉल S1 dash घेऊ. So S1 dash is equal to Q1 upon T1. Here we will get negative sign. का? कारण की Q1 amount of heat energy system ने absorb केलेली आहे, म्हणजे सराउंडिंग ने काय केली असेल ती रिजेक्ट केली असेल, आणि रिजेक्ट केली असेल त्यावेळेस आपण काय घेतो निगेटिव्ह साइन. So here we will have S1 dash is equal to minus Q1 upon T1. Again for C2 to C3 change in entropy 0. Okay, S2 dash घेऊ आपण सराउंडिंग साठी, कारण की एडिबॅटिक प्रोसेस आहे, एडिबॅटिक प्रोसेस साठी चेंज इन एंट्रोपी काय असते 0. C4 C1, आता C4 C1 Q2 अमाउंट ऑफ हीट एनर्जी रिजेक्ट केलेली आहे, कशाने सिस्टमने, पण ह्याने रिजेक्ट केली तर ते कुठे जाईल सराउंडिंग कडे. त्याच्यामुळे ड्यूरिंग C4 C1 चेंज इन एंट्रोपी, ओके सॉरी C3 C4 चेंज इन एंट्रोपी S3 dash is equal to plus Q2 divided by T2, कारण Q2 amount of heat energy surrounding कडे आलेली असेल. Now last, during C4 C1 change in entropy S4 dash is 0. For whole Carnot cycle, change in entropy of surrounding delta S dash. Again addition करावे लागेल आपल्याला. मग इथं आपल्या इक्वेशन मध्ये काय होईल की मायनस Q1 divided by T1 plus Q2 divided by T2. But for Carnot cycle, this equation holds. Q1 divided by T1 is equal to Q2 divided by T2. So if you put that in equation, this above equation, okay, you will get change in entropy of surrounding is again 0. Okay, now here you can write this equation, कारण की हे इक्वेशन कशाचं आहे युनिवर्स साठी. युनिवर्स मध्ये कुठेही रिव्हर्सिबल प्रोसेस झाली, ओके, त्या रिव्हर्सिबल प्रोसेस मध्ये चेंज इन एंट्रोपी काय असणार आहे 0. कशाची सिस्टमची आणि सराउंडिंगची. सो दिस इज द इक्वेशन फॉर universe. So change in entropy for reversible process which are taking place in the anywhere in the universe is 0. Now we are going to see next point, change in entropy during irreversible process. Okay, so this is again principle of increase of entropy. For this we are going to study again, if you have Carnot cycle like this, but again in this cycle C1, C2, C2, C3, C4, C1 and C1, C4, C1, all these four path, out of this four path you can take any one path which is not reversible. Means what, आपण जर C1 पासून C2 कडे गेलो तर C2 पासून परत C1 कडे येऊ शकतो. ओके, याच पाथने. जर समजा आपण हा जो पाथ आहे, ओके, या पाथला आपण काय केलं, हा रिव्हर्सिबल नाही असं दाखवलं. त्यासाठी इथे काय केलं असेल लाईन काढली. सो हियर C1 C2 is isothermal expansion at temperature T1, amount of heat energy Q1 absorbed. C2 C3 adiabatic expansion. C4 C1 is not a reversible path, so this is not reversible path. Now during this case again here amount of heat energy rejected Q2 at temperature T2, our all the equations are same. सिस्टीम साठी जर आपण पाहिलं तर आपले सगळे इक्वेशन्स सेम असतील. काय S1 डॅश काय असणार आहे, Q1 T1, S2 डॅश 0 असणार आहे, S3 Q2 T2, चेंज इन एंट्रोपी हे येईल आपलं. ओके, Q1 upon T1 minus Q2 upon T2. बट दिस इज नॉट अ कार्नॉट सायकल. ही कार्नॉट सायकल नसेल, कारण की एक पाथ काय केलेलं आहे आपण रिव्हर्सिबल नाही असं दाखवलं. जर हे रिव्हर्सिबल पाथ असतं तर ती कार्नॉट सायकल असते ना. आपलं जे इक्वेशन आहे Q1 upon T1 is equal to Q2 upon T2 हे तिथं अप्लाय झालं असतं, पण आता ते इक्वेशन इथं अप्लाय होणार नाही. ओके, सो इफ Q1 upon T1 is not equal to Q2 upon T2, what does it mean? It means Q1 upon T1 minus Q2 upon T2 is a positive quantity. Why? Q1 ही काय अमाउंट ऑफ हीट एनर्जी ऍब्सॉर्ब आहे आणि Q2 ही काय अमाउंट ऑफ हीट एनर्जी रिजेक्ट आहे. ओके, मग कोणती थर्मोडायनामिक सिस्टीम ज्यावेळेस हीट एनर्जी ऍब्सॉर्ब करेल DQEOD, त्यावेळेस त्याच्यातली काही हीट एनर्जी ती काय करते, एंट्रोपी इन्क्रीज करायला पण यूज करेल आणि काही हीट एनर्जी इंटरनल एनर्जी इन्क्रीज करण्यासाठी यूज केल्यामुळं सगळेच्या सगळे तिला रिजेक्ट करता येणार नाही. ओके, समजा 1000 कॅलरी हीट ऍब्सॉर्ब केली तर 1000च्या 1000 रिजेक्ट करणार नाही ती सिस्टीम, 1000 मधली कमी करेल काही. ओके, 900 करेल, 800 करेल, डिपेंडिंग ऑन फिजिकल सिच्युएशन. Now here Q1 upon T1 is not equal to Q2 upon T2. That's why we can say Q1 upon T1 is positive than Q2 upon T2, is greater than Q2 upon T2, not positive. So in that case we can say delta S during IR, now IR represent irreversible process, is greater than equal to 0. So change in entropy during irreversible process is positive. Now in nature, निसर्गामध्ये जेवढे काही प्रोसेस होतात थर्मोडायनामिक प्रोसेस, या सगळ्याच्या सगळ्या रिव्हर्सिबल नसतात. कारण रिव्हर्सिबल प्रोसेससाठी खूप आयडियल कंडिशन्स ठेवावे लागतात आपल्याला. ज्या स्पॉन्टेनियस प्रोसेस आहेत त्या सगळ्या कशा असतात, इरिव्हर्सिबल प्रोसेस असतात. मग जर सगळ्या प्रोसेस इरिव्हर्सिबल असतील तर त्या केसमध्ये काय असणार आहे, चेंज इन एंट्रोपी ही काय असणार आहे, ग्रेटर दॅन इक्वल टू 0. ह्याचा अर्थ काय असणार आहे की एंट्रोपी ऑफ द युनिवर्स टेंड्स टुवर्ड्स मॅक्सिमम. रिमेंबर, entropy of universe tend towards maximum. What does it mean? It means युनिवर्सची जी एंट्रोपी आहे ती टेंड म्हणजे काय, एक तर कॉन्स्टंट राहते किंवा वाढते पण कमी होत नाही. So entropy of the universe is always tend towards maximum. So this is the statement of second law of thermodynamics. Now with this we finish our lecture over here. Okay, now in next lecture we will see the remaining part.